Okay, we are live now. Thank you.
Okay. Welcome everyone to the pizza seminar. Today's speaker is Daniele Spinoso. He's currently a postdoc in the University of Insubria in Italy. He has a bachelor in physics and a master's in astrophysics, also from the University of Milano. And then he did the PhD in FEFCA in Teruel. Yeah. And then he did 1 year of research assistant in Donostia, in the Donostia International Physics Center, and then 2 years of a Xinmu Fellowship in Tsinghua in Beijing, China. And today, well, he's going to talk about his expertise, which is in modeling and formation of the evolution of the massive black hole, also analyzing photometric data and building AGN luminosity functions. So, Daniele,
thank you very much.
The floor is yours.
Okay. Hello, everyone. I'm very happy to be here. Thanks for the opportunity to organize us, and thank you for being here, of course. Thanks for the introduction. Yes, I am a postdoc at the Como Lake Center for Astrophysics, which is up. Maybe we can wait for the eventually. So yes, my expertise is modeling the formation and evolution of massive black holes in cosmological environments. And as I don't know which is the background, I'm gonna give a quite broad outline of why this topic is interesting and the methods that we use. Then I'll show a collection of results and I'll leave you with some conclusions. So let's start. The motivation for this work mostly comes from the observation of very massive and actually very luminous quasars at high redshift. Here I'm showing a collection which is not updated. The picture really changes very quickly nowadays, but this is a collection of luminous quasars observed at very high redshift as compared to the population of quasars that we observe at lower redshift, for instance, with SDSS. And so you can see these purple dots and orange squares, which show luminosities of 10 to the 46 and above. This means 10 to the 13 luminosities in solar, like 10 to the 13 more luminous than our sun, which is already impressive. And these luminosities, we thought they are associated with black holes of masses of 10 to the 8 and above solar masses. So these are really monsters, okay? But not only these properties are striking, probably the most striking part is that they are observed when the universe was less than 1 gigayear old. So the main question here is how is this object basically formed? And since the first black hole seeds, so the first object from which they started, may have formed really early in time, basically we want to know how they grew up so quickly and which were the first seeds of these objects. And not only this, recently you may have heard JWST is discovering a lot of different sources, among which there are these so-called little red dots, these little points here that I'm showing a direction, which at least a fraction of which is thought to be associated to AGN emission again, but not of the same kind of the ones that I was talking about before. Let's say a more typical AGN, so a fainter AGN with a less massive black hole. Still, these objects are quite abundant with respect to what would be the extrapolation of the AGN luminosity function at faint luminosity. So they are really at least 1 order of magnitude, we think, above this. So there is really a huge population of these objects, and so this prompts other questions. So do these objects come from the same processes as the previous ones? How do they evolve with respect to their host galaxies? Do they only form at high redshift, or do they form throughout the whole history of the universe, and so on? So normally, the answers to this question start, of course, like from the seeds, as I explained, but the kind of seeds that we imagine come in 3 different phases. Starting from low mass to high mass, we have either the formation of the first seeds as remnants of the first stars, in a scenario that we name light seeding. And these objects are thought to have sort of 100 solar masses. They probably are or 10,000 solar masses. They are probably common. We don't really know. There are hints of these objects actually being very common recently. They require some specific condition. I'm going to go into more details here in a few slides. They also form a high redshift, but not as high as LGBH, we believe. And so the idea is which is the balance with respect to these two channels, for instance. And going even higher in mass, we have heavy black hole seeds with masses of 10,000 to 100,000 solar masses. These may be even more rare than the intermediate mass ones. Also form under given conditions, also high redshift. And finally, we have the extremely massive seeds, which may form, we believe, after the merger of gas-rich galaxies at high redshift. So this picture covers a wide range in mass. So if we look at the typical halo mass where these objects are expected to form, we go from mini halos at very high redshift, which I define as 10 to the 6 to 10 to the 7 dark matter halos, where the first stars are believed to form, up to Milky Way type halos, which are 10 to the 11 solar mass. So this is really a wide dynamic range. And if we place all our questions on one side, and what we would like to know in order to model all these processes in such a wide dynamic scales, we see that we have quite a stringent constraint. So we want to know where they form, for instance. We want to have high mass resolution because we want ideally to resolve the first mini halos, also in large volumes because we want to model the whole population. And so we have kind of a big list of requirements, let's say. And this is obviously, at least for the moment, very difficult to obtain with hydrodynamic simulations because these simulations are expensive in terms of computational cost, so they can only access generally small volumes. So what was our answer to do all this? Well, we resort to a numerical tool, which is called generally semi-analytic models. And what are these? So broadly speaking, semi-analytic models are based on dark matter merger. So either one run a dark matter only simulation and extracts the halos from this simulation and then connects them in time into what is called a merger tree, which basically follows the evolution of halos from when they form down to their descendants at lower redshift. Or merger trees can be built also analytically from extended press and checked formalism, for instance. But in general, we need a backbone, which is basically a merger tree of dark matter halos. And then the analytic model come in and basically paint barriers on top of these halos and follow the evolution. Here I'm showing as a sketch the main components that are tracked by a semi-analytic model, which are generally hot gas in form of a spherical atmosphere, cold gas in form of a rotationally supported disk, and obviously stars inside this cold gas disk. Okay, so why these tools are in some way more, fitted for what we want to do? Well, basically, since they track these components analytically, they don't need to resolve the physics in such high detail as an hydrodynamic simulation, but they only follow basically the evolution in time of these quantities. And this allows to basically simulate very large volumes, but also repeat very efficiently different runs and explore different model parameters, for instance, or different models, different physical models themselves. So this is actually an ideal tool to have statistically significant results on large volumes. Among all the possible semi-analytic models that are there in the literature, we started this work in 2016. And at that time, L-GalaxiesBH 2015 version was available. And this was actually ideal for us because on top of having already included a detailed model for galaxy evolution, so basically the evolution of cold gas stars and so on inside galaxies, it was also designed to be run both on Millennium 2, here I'm showing, and Millennium simulation. So you can see by a combination of this relatively high mass resolution and large box, and not so high mass resolution, but significantly larger box, we could access, let's say, a wide enough dynamic range and a large enough volume. So as I said, L-GalaxiesBH included a lot of physics and still includes a lot of physics for basically modeling the evolution of galaxies. Here I'm just showing a collection of the results regarding galaxies. This is a stellar mass function at different redshift. In red, the model prediction, and in blue, a collection of data. So you see the model already does a good job, a pretty good job about modeling the evolution, let's say, of galaxy masses through time, down from redshift 3 down to redshift 0. A similar thing for the H1 mass function, so the gas content in galaxies, the evolution of the star formation rate as a function of redshift, the mass metallicity relation, and this basically star formation in sequence, so stellar mass versus star formation rate. So it is already, it was and it is already a model that performs well, let's say, in most of the observables related to galaxies. What was missing at the time, and what this talk is about, is the presence of massive black holes inside these galaxies. So we started a branch of these galaxies 2015, which was significantly modified, including seeding prescriptions, for instance, evolution of spin, gas accretion, dynamical evolution of black hole binaries, and wandering black holes outside galaxies. By the way, a significant part of this was actually developed by Davide Schiarovi-Alba, which is a person here at the IFE, in case you want to talk to him. And yeah, so we ended up with a model which is very complete also on the massive black hole modeling part. And just to give you, again, a collection, we can reproduce the spin of black holes at redshift close to 0. Black hole mass functions, both the total population and the active population of black holes, AGN luminosity functions at a wide redshift range, the local stellar mass to black hole mass relation, and interestingly also provide some predictions for the gravitational wave background, which is being basically currently tackled by, for instance, PPA experiments. Okay, so on top of all these, Galaxies is also equipped with the recipes to build light cones. So it can be used to simulate actual galaxy surveys. So a given light cone, a given solid angle in the universe, and a given redshift dependence, let's say, or on an all-style survey, as I'm showing there. And sorry for being this, like adding so many things, but crucially for this work, we can also connect simulations that are high resolution and small box to larger and larger simulations, basically by using the outputs that L-Galaxies obtains on smaller simulations as inputs for the evolution of structures and galaxies and so on inside larger simulations. So basically, we can extend the physical modeling that we can track on small simulations down to the largest scale possible. Okay, so if you remember this picture that I painted before, with the galaxies, we kind of cover most of it. And so let's see how we do with the black hole seeding model, which is basically the topic. Okay, so as I said at the beginning, we have these 4 channels generally, and all of them are modeled in the galaxies. For this specific model, we need high resolution, so we focus on the Millennium 2. And just briefly, every channel is modeled in its own way, so we cannot track mini halos. You can see the minimum halo mass which we can access is 10 to the 7, which is slightly higher. So for the light seed, we have to basically build a subgrid model and form them in an unresolved way before halo form, or well, before halo can be resolved in 2. Intermediate mass black hole, which here I named runaway stellar mergers, because we think that the origin of these black holes come from the runaway, so very efficient mergers of stars within and black holes within nuclear stellar cluster high redshift. The halos in which these objects form are resolved, so we can place actually physical constraints on the environment that these objects should be living into when they form black holes. Similar thing goes for the heavy black holes, which we call direct collapse black hole here. Again, they are resolved. We can place physical constraints and we can track actually the environments where they form. And then, of course, we can follow galaxy mergers, and we can also model merger-induced direct collapse black holes. Okay, I jumped a slide here, but anyway, you get the picture. We have a complete model for black holes. Just a few details more. So this is the mass range of halos that are newly resolved in Millennium 2. So what we do, as soon as we find a halo, we go back in time, we sample an IMF for top 3 stars, We form a black hole, and then we let evolve it back to the time in which we resolve it. We can form one black hole in the halos or multiple black holes instead. Basically delays the cooling of gas until the point in which either a halo or the gas inside the halo is dense enough to form a nuclear stellar cluster at the center, or the cooling is completely stopped, and so you have basically a gas cloud which never forms stars, which monolithically collapse into a single massive object. Okay, so we track again the UV illumination and the metallicity around halos, because again, the metallicity works in an opposite way as the UV illumination, accelerating cooling. So with the balance between these two properties, we actually form these two kinds of seeds in an informed way, let's say in a physically motivated way around halos. Okay, so I'm not going to go into details here, but it's just to let you give you the picture of the balance between these two fields and the dependence of the formation of black holes. And then again, as I was saying, we can track mergers, so we can select the specific condition under which we believe supermassive seeds can form in galaxy-rich mergers ahead. Okay, so all this gives us a seeding model in which these channels can happen all at the same time. Of course, we assume that if one kind of black hole forms, the other kind won't form. But this is an assumption that can be relaxed, for instance, in the future. But the main point here is that very few models can model all of these all together in a cosmological context and then follow evolution down pressure zero. So let's see what happens when we place these in a cosmological box, and in this case, they remain into volume. So here I'm showing the number density of black holes as a function of redshift split into different seed types. Pink is light seeds, and you immediately see that they clearly dominate. Merger-induced direct collapse are absent, so we don't find any biased environment where gas-rich merger are favorable to the condition to the formation of these massive black holes. Interestingly, the dotted line here are the newly formed black holes of each type, and you see that these lines stop at a given point. We don't impose this; we just check for the conditions to be verified. So basically, at some point, the conditions are not good anymore for black holes to form in our box. And so this produces basically an end to the black hole seeding prescription, let's say, or if you want to see this as a black hole seeding epoch at redshift, this epoch at some point ends in our model, which is interesting because then if we let evolve this population only through mergers and gas accretion, they actually match the local constraints. So we have already an answer to one of the questions that I was asking at the beginning. So, do black holes form at any redshift? Do we need, only massive seeds at high redshift, only light seeds? So this is already a kind of an answer. Light seeds probably prevail over the overall population of black holes. And we have different seed types that contribute to the whole population, but they only form at high redshift, at least in our model. Interestingly, since we have access to the whole box and so also to the positions of halos, because Millennium 2 is a cosmological simulation, we can actually track the environment of black hole seeds when they form. So here I'm showing just a sketch, a picture of two different kinds of environment that we find. One is for direct collapsed black holes, so the heavy seeds, and one is for intermediate mass black hole seeds. So you can see this is the projected mass density, dark matter density around black hole seeds, and you can see that this is clearly already by eye. You can see it's a clearly more populated environment as this one. Here you have the star formation rate density is not really clear, but here you have just few galaxies. Here there are many more. The UV background field around black holes and the metallicity environment. So it's interesting to see the differences in the environment as they are basically associated to different formation channels. In particular, the underlying model by which heavy seeds form in our model is based on this picture called the synchronized halo pairs or closed halo pair or something like a variation of this. But the fundamental idea behind this is in a halo that is probably hosting the formation of a direct collapse black hole, you would need to stop entirely star formation. So you would need UV light, and a very strong, actually, UV light to completely photodissociate this halo. And this light may be coming from a massive neighbor, which is actively star forming. Okay? But not only that, you don't need metals to be polluting these. Otherwise, cooling can accelerate again and fragment gas inside this halo, and so you don't have a direct collapse black hole or a heavy star, right? So you really need to find this specific time in the life of this atomic cooling halo where it is illuminated but it's not polluted. So you have this synchronization in time and space between halos in order to pollute. And what we find is that by only requiring low metal pollution and high UV flux, basically we have a bias in the selection of these environments, which it's not difficult, of course, to imagine this. This kind of situation can be found in, it's more likely to be found at least in more dense environments. So if we look at the typical distance in terms of virial radii, where the nth neighbor is found around the halo, we have a measure of how densely populated is the environment around a given object. In red here, you see direct collapse black holes, and you clearly see that they deviate from the general trend. And so they actually statistically live in a more dense environment than other black hole seeds. And this is only imposed by the formation requirement. So we have an imprint of that. So this is something that ideally could be also observed, right? Staying on the topic of heavy seeds, recently there has been a lot of interest in them because of the high masses that are observed at very high redshift, for instance, from JWST. I'm not talking about the monsters that I was introducing at the beginning, but more of a sort of an intermediate black holes, but at extremely high redshift, 11, 12, and so on. And so here I'm showing just an idea of what recent work suggests. So starting from different types of black holes, you need a given rate of growth. So starting from light seed, is likely that you would need a very quick growth, which we name super Eddington growth, because it works higher than the theoretical limit given by the Eddington limit. While if you start from more massive seeds, you may relax this condition of having very quick growth and grow at Eddington or even sub-Eddington rates. Same thing goes. And not only this, very recent work has suggested that heavy seeds may be also at the core of the formation of these little red dots that I was mentioning. In this idea, a very massive object, of the order of 10 to the 4, 10 to the 5 solar masses would start basically evolving as a very massive star, which will produce a compact core around which very efficient gas accretion in a matter of a few mega years produces a very massive star. So the idea is this actually true on a cosmological box? So maybe it can work for an object, but can we actually form little red dots via heavy seed, or in general, massive black holes via heavy seed? So we tested this idea. So, as I mentioned at the beginning, follow the dynamical evolution of black holes once they are formed. So we follow them as wandering black holes around galaxies and inside the dark matter halo. Once this phase ends, we follow them inside the galaxy when they pair to each other before forming a nuclear, eventually, a nuclear binary black hole bound by their respective gravitational potential. So with all this feature, we can actually follow and track what happens to that tiny halo that was synchronized to the large massive neighbor. And what we see here is if we split the number density that I was showing you before of black holes as a function of redshift as nuclear, pairing, and wandering. So continuous lines are nuclear, pairing black holes which are already inside galaxies and slowly infall into the center, and wandering black holes, we see very different evolutions, pathways between light, intermediate, and heavy seeds. In particular, if you follow these red lines, you see that the wandering black hole population, which was born as heavy seed, is the only population for which the wandering black holes are actually more numerous than the nuclear one. And this really you can see here, the unweighted, the intermediate mass black holes are always subdominant, just as in the light case. This is even more clear if we follow in time the fraction of each type, so nuclear, pairing, and wandering as a function of redshift for each seed type. And just focus here on the red lines, you see wandering black holes become already 35% or so at very high redshift, and already 50% by redshift 4, if we focus on the heavy seeds. So this would not be really an issue, because the origin of this is basically that the halo that is orbiting around the massive neighbor basically gets disrupted, and the black hole stays around the galaxy orbit. This is shown by the disruption. This is basically the ratio between this line and the black line. And you can see that heavy seeds really tend to be disrupted very quickly as compared to light and runaway stellar mergers. Again, this is not in theory an issue, just how the model and physics work, but it is actually problematic if you want to form 10 to the 6th, 10 to the 7th, 10 to the 8th solar masses via this channel. So here I'm showing the black hole mass of this wandering black holes as a function of redshift. And you see that heavy seeds never manage to get to a few 10 to the 5 solar masses. So we cannot form massive black holes with this channel. At least if they form in a synchronized pair of halos. So we need another method in order for heavy seeds to be a realistic explanation for the black holes that we observe at high redshift. So what about the extremely massive seeds? So we can check if those can be an answer. And so what we did was to test this merger-induced scenario, not only in the millennium, as I was showing to this point, but actually grafting, as I was telling you before, the results of the millennium into the, millennium 2 into the millennium. And so we have a large volume with a physically motivated black hole seeding, and we can repeat the exercise that we did. Again, we see the light seeds are probably dominant. This is no surprise. But this is interesting, actually. The first condition for forming a merger-induced black hole, a super heavy seed, they say, can be actually realized or verified even at very high redshift on the millennium volume. So on a large volume where we have more statistics about biased environments. And not only that, these black holes, the merger-induced one, actually efficiently mix with other types. So they really have a rich merger history, even though they are subdominant in terms of number with respect to the other light seed types. So in theory, in practice, well, at least from what we see, we have enough massive black holes here to explain, or at least suggest that some of the most massive black holes at high redshift may be the result of a very gas-rich merger. If then we follow these black holes down to redshift 0, we can see where they are in the stellar mass to black hole mass relation. And this blue line basically tells you that some of, in the history of these black holes, at least once there was a merger-induced formation. And so you can see that these objects are really belonging to the most massive objects, both in terms of mass and black hole, stellar mass and black hole mass at redshift 0. So eventually, if we look at the most massive early type galaxies in the local universe, we may have that a fraction of them is formed by this channel. Finally, I want to give you a few words about a work that was recently carried out by a student, a PhD student at the DIPC Institute, Diego Herrero, about the simulation of little red dots in this context of the galaxies and black holes. So main point, I'm again not going into the details here, is that these objects are challenging our understanding of early galaxy formation and evolution, because they show this sort of V-shaped profile. Here I'm showing a spectrum from JWST, from Green et al. 2023. So you can see in black the spectrum, which has these two clear components, and people at least in the early phases of these discoveries, were struggling to understand whether this would come from an obscured AGN with unobscured AGN, so a combination of two AGN, here shown as red obscured AGN with some galaxy light and star-forming galaxy light. So it really was not clear what these objects were, and it is still unclear. But many more models, rather than just a combination of galaxy and AGN, have been proposed so far. But we wanted to test this idea of little red dots being a combination of galaxy and AGN on a cosmological context. So we built a light cone as a beginning. So we simulated what JWST would see. And since we are able to basically decide the solid angle that we observe or actually simulate, we built a much larger area than JWST would observe, but still with JWST photometry, so that we could build a comparison, a fair comparison with JWST observations, but with larger statistics. What Diego did in particular was to add the modeling for the emission that we think an AGN would produce. So he added basically the emission from the accretion bees, from narrow line and broad lines, and then the reprocessing of this light from a UV torus. Again, I'm not going into details here. The emission from the AGN bees would be this blue line here, and it's actually mutated from another work. And then Diego modeled the obscuration from the dust and so on, depending on the inclination, of course, because sometimes light from the central engine is not reprocessed by dust around the AGN. And all these was actually coupled to the model that is already present in L-galaxies to produce galaxy spectra. With all these, we could then simulate JWST photometry and then build the same selection that observational work do, but in a simulated environment. And so we reproduce the colors. So red points here are observation, blue dots is the distribution of the sources that Diego found in the light cone, and a compactness plot as well. And so we could then build some statistics based on a realistic selection function. So what we found is here on the black line, little red dots account for a fraction that depends, that varies with redshift, and it generally varies between, say, few percent and 40%, depending on redshift. Similar thing for the AGN fraction within the little red dots population. But interestingly, most of the AGN are actually little red dots. So sort of 80, 70, 80% across all redshifts. So this already, at least on the basis of this model, tells that probably the explanation as AGN of little red dots is actually valid on a cosmological context. But then we could do something more, which is generally difficult to do in observation. So we could see where these objects live in terms of stellar masses, halo masses, black hole masses, and AGN luminosity. What we found is that little red dots here in red tend to live generally, well, there are actually two classes. One is hosted by massive galaxies, especially at high redshift, or low mass ones. But non-little red dots here in blue are preferentially hosted in low mass galaxies and low mass halos. Hosted in, well, tend to be associated with small black holes at all redshifts, and so less luminous AGN, which is kind of interesting, and also tells you somehow that probably we are observing little red dots as a specific population, but the reality is actually more complex. There may be more than one population. There may be a component of luminous little red dots and a more predominant population of faint AGN little red dots, and so on. Interestingly, a lot of papers have showed that little red dots, or in general, AGN observed by JWST are overmassive with respect to the local relations. And here we are showing this analysis at different redshifts. So stellar masses on the X versus black hole mass. Little red dots are in red, and the AGN is this dark red. So what we found is that little red dots AGN actually tend to be less massive or less luminous again than non-little red dot AGN, and which is interesting because if we are observing very massive little red dots, as this data show, we are probably only seeing the tip of the iceberg of this population. But there is a lot of other objects that we are not seeing because of probably just observational limits, for instance. And this is everything I have. I'm not going to go through all the conclusions, but if you want to ask some questions, I'm happy to answer them. Thank you very much.
Thank you. Very nice talk. Questions?
Is dark matter thought to be a relevant component of the matter of the black hole?
Okay. So yeah, the question, if I understand it correctly, is how relevant is dark matter in the mass of the black holes that we model? In our model, we don't follow any channel that is related to dark matter for the formation of black holes. We are just trying to see if baryonic physics can account for these objects, let's say. But you're right, there are interesting possibilities. If you assume, for instance, primordial black holes or this kind of objects, yeah, it can be an update to this model. That may be interesting.
These results eliminate the need of primordial black holes.
I see there is a big cosmological issue. Okay. The quick answer is no. They don't eliminate the need for primordial black holes. Actually, I think the main point of this is that we don't need to restrict one channel for forming AGN or black holes in the universe. It is entirely possible that some of the objects that we model it is not incompatible with primordial black holes and dark matter black holes. But yeah, it can be added to the model in some ways. Yeah, good, interesting, actually.
Yeah, thanks. This might be a naive question, but if I understand correctly, your L-GalaxiesBH is running cross processing, like once you have convergent trees and volume simulation. You think about using some of the latest cosmological simulations that have much larger volumes, much higher resolution. It's the only thing you need divergent trees. Yes, there are some very nice.
Yes, it's a very good point. So I didn't show it because it's not really finished work, let's say. But L-Galaxies black hole was modified already by David to include TNG merger trees. So it can be run already on the TNG suite. And then, yes, once the merger trees basically are in the correct format, you can apply L-Galaxies black hole to basically any cosmological simulation that you want, or not, or you can build any Red-Schechter merger tree and then apply L-Galaxies to it. What we found is that you really need to recalibrate your model because different resolutions give you different physical dependencies, let's say, with of some models. So you may want to just not blindly apply the model, but then also take care and recalibrating it. Yeah. Yes.
I'm just a little surprised about the resolution of the simulations. Like they could reproduce the spin distribution of massive black holes, like because I think the current observational distribution, most of them reach the upper limit, which and they come from the accretion of the supermassive black holes. It's the but here, I think in your simulation, you use the main come from the mergers, and the things I don't quite understand why.
Yeah.
So how can they reproduce and have your simulation includes the accretion dynamic of it?
Yes. So I'm not sure if I understand your question is how can we get to this spin distribution with the model that we have and the resolution that we have?
Yeah.
Okay. Okay. So again, for this model was developed by David. So if you have detailed questions, it's his fault. No, I'm joking. But I mean, if what I can tell you is that in our model, the accretion is coupled to the spin, okay, in such a way that depending on the morphology of the galaxy, you may have either chaotic accretion of gas or a coherent accretion of gas, and this would in turn produce a spin up or spin down of black hole, and a gas can be accreted onto the black hole. We can actually track the spin evolution as coupled to the growth. Now, if you were asking about the resolution itself, as you see, like we can somehow be sure of our results, let's say on black holes that are of the order of 10 to the 6 and above solar masses, and this would be hosted likely in slightly less, so 10 to the 10 galaxies in terms of stellar mass and orbit, right? So these are objects that are well resolved in our simulation. So up to our, let's say, understanding, this object, the evolution of these objects is actually well tracked. So it's not a result of spurious events or these kind of things. I don't know if I answered that.
I'm not sure I got the answer to the question. Did you understand what is the nature of this shape or the spectrum?
Yes, actually, yes. Of course. Sorry, I didn't go into that in a lot of details, but I have a backup slide that I think is very interesting. So, well, let's start from here. Okay, so this model is based on the idea that AGN and galaxy contribute to the photometry, and then AGN would be contributed to the blue part if it's not obscured. So, you have this typical shape of an AGN. While if it is obscured, this light is reprocessed and it produces a black body in the infrared, right? This is the general idea. On the other hand, galaxies, as usual, if they are star forming, they tend to be blue. Otherwise, if you have an old stellar population, you tend to have a strong bulbar break, and you have this kind of bumpy feature as well. So you have basically the contribution of these two things in the infrared optical, so bulbar break or the dusty torus of the AGN, and or an obscured AGN and dusty, star forming galaxies on the other side. So here you can see that the masses of little red dots, let's focus on these, are the black hole masses are generally lower than non-little red dots. So what you expect in terms of luminosity is that the blue part of the AGN is actually lower, okay, in the photometry than non-little red dots. So if we go here, this is the median photometry is a function of redshift from right to left and stellar mass. So especially here, if you concentrate here, you can see little red dots have this shape, right? While non-little red dots tend to be more linear. So this is a combination of the bulbar break of galaxies and the AGN part. What happens is that more massive is the black hole, more luminous is the AGN, less evident is the bulbar break of the galaxy. So in this sense, our model, which only considers galaxies and AGN, is telling you that little red dots tend to be less massive because we select them from the V shape. And so we tend to select low mass black holes, which are less luminous. Yeah. These pictures varies with redshift, but let's say it's clearer at the highest redshift, at the lowest redshift and highest mass be.
Sorry, so related to that, the observations from James Webb, the lowest redshift is around 4.
Mm-hmm.
But in your simulation, what is the lowest redshift where you find these little?
Yeah, it's a very good point as well. So we built the simulation to go from redshift 4 to redshift 11, 13. But actually, we can identify these objects in a normal simulation and then track them down to redshift 0. So my expectation is that if you apply this selection function that is used to select object at this redshift, at low redshift, you will select a different population just because you have different features at the same, let's say, fixed wavelength in redshift. But you can play the exercise of selecting these objects at high redshift and then following them, exactly them, down to redshift 0 and see how they evolve.
Do you expect to see them at low redshift?
Yes, but they are probably a different kind of object at lower redshift. If you want to know these objects, what
Another question?
I was, keeping it for later, but I can ask. I have two questions, and is how to prove the results observationally. And I took snapshots of things. One, you said about the heavy seed black holes. You said, first of all, that the fraction of them being one billion should be higher. Right. So observationally, if we find a high fraction of wandering black holes, maybe that the black holes form from heavy seeds.
Yes, I mean, I'm not against black holes forming as heavy seeds at all. I'm just saying that if they form in couple and the heavy seed is in the low mass satellite, it's unlikely that the seed would sink to the center very efficiently and then become very massive in a very short time. So this can happen, and it's great that observationally there are a lot of hints about wandering black holes. Personally, if I look at this model, I would struggle to understand how these wandering black holes then become the most massive quasars that we observe at the redshift. But this is not incompatible with finding a lot of wandering black holes. Actually, that's great. It's the proof, let's say, that we have black hole formation spread around in a given kind of friend, let's say, I would say.
And the other observational thing I found is that you said that these heavy seeds are in denser environments. So we investigate the environment of, say, the medium mass black holes observationally. We can infer whether they form from heavy seeds or light seeds.
Exactly. Yes, this would be one of the reasons why we built this JWST light one actually was then to select the most massive AGN and then go look at their environment and link them to the formation channel of these black holes and see if we already with JWST we can link how dense an environment is with the formation channel of the black hole. Yes, that's a very good point. Yes.
Sorry, so related to that, so you have these denser environments, but you need low metallicity.
Yes.
So it has to be like higher redshift. So at some point, this is going down, right?
Yes, it stops as I like let me show you again the plot. Sorry. Yeah, so you can see here you really, as you said, you need low metallicity, and this happens only at high redshift. So as soon as the companion produces some stars and some winds, some powerful winds, you don't have any more low mass companions that can form direct collapse. So in this model at redshift day 9.5, you stop forming direct collapse black holes. Yeah.
Like, sorry, just about this thing. So, but then, so they stopped at redshift 10, but they started at redshift 14.
Yes. Yes.
But then, so all these things were black holes found at redshift like, I don't know, maybe 11. Then these kind of come from the ones that started at redshift 14.
Yeah, I mean, you're saying that between redshift 14 and redshift 11, there are just a few years probably, and so you wouldn't have time. Yes, yes. Especially if these black holes are centrals, because again, they would be just around halos and be disrupted easily, and they don't grow enough. So it's likely that they are. I mean, if heavy seeds form in close halo pairs, then it's likely that they are not JWST AG.
Okay, so thank you very much. You can thank the speaker again.
They were sitting online.
No, yes, I don't. No.
Okay.
No.
Okay.